All right, today we're going to dive into the really strange and honestly fascinating world of stationary waves. Now, you probably think you know what a wave is, right? But these are a completely different beast, and they're hiding in plain sight in everything from your guitar to your microwave, powered by some truly wild physics.
I mean, seriously, think about it for a second. When you pluck a guitar string, it hums, it makes a sound, but the wave itself just seems to stay put. It doesn't travel down the string and shoot off the end. So, where does all that energy actually go? It's this simple question that gets us right to the heart of what makes these waves so incredibly special.
And that's really the fundamental difference right there. You see, a normal traveling wave, like sound coming from a speaker or light from the sun, is all about transportation. It's carrying energy from one spot to another. But a stationary wave? Nope, it's the total opposite. The energy gets, as the source material puts it, bottlenecked. It's basically trapped, just held right there in place. So this brings us to our first big secret. A stationary wave is what you get when two identical waves smash into each other while traveling in opposite directions. And the result is this new wave that doesn't actually transport energy anywhere in a net sense. So, get this, the energy isn't lost, and it's not going from point A to point B. Instead, it's just shuttling back and forth within this tiny confined space. It's always moving, for sure, but its overall position is totally fixed, which is exactly why we call it a standing or stationary wave. Okay, now we get to the really juicy stuff. Let's bust a huge myth about the anatomy of these waves. We're going to take a closer look at the parts that seem to be doing absolutely nothing at all, the nodes. So, your textbook would tell you that a node is a point with zero displacement. And if you look at a vibrating string, that seems right. The nodes are the spots that are just perfectly still. They don't move up, they don't move down. That's what we see, but it is definitely not the whole story. And this is what pretty much everyone assumes, right? A point of zero movement has got to be a point of zero action, just a total dead spot on the wave. But that could not be further from the truth. And here it is, the big reveal. At the exact point where the particles aren't moving at all, the pressure is going absolutely nuts. Imagine a sound wave in a tube. At the node, the air molecules aren't moving back and forth, but they are getting squeezed together and pulled apart like crazy. So even with no movement, the node is actually a hub of maximum pressure. Okay, so let's check out the node's counterpart, the antinode. This is the part of the wave that's impossible to miss. It's the point of maximum movement, where the string is swinging up and down the most wildly. It's the star of the show. And here is the truly mind-bending twist. At the spot with the most movement, the pressure change is zero. Nothing. The particles are moving the fastest, sure, but they're doing it in a region where the pressure isn't changing at all. It's the complete inverse of the node. Just wild. And this table just lays it all out so perfectly. At a node, zero movement, maximum pressure change. At an antinode, maximum movement, zero pressure change. It's this hidden inverse relationship that powers all the physics we're about to see in action. But hold on, the weirdness is not over yet. It's not just about what's happening at these single points. It's also about how all the particles move together in this strange, perfectly synchronized dance. This is what our source calls the phase trick, and it's pretty cool. Unlike a normal wave where particles are kind of at a step, here it's different. All the particles in one segment, between two nodes, they move like a single unit. They all go up together, they all go down together. At the same time, the segment right next to it, it does the exact opposite. When one side goes up, the other goes down, perfectly out of phase. So, okay, we've talked about trapped energy, high-pressure dead spots, and these weird synchronized particle dances. This all might sound super abstract, but it has a very direct impact on something you probably use every single day. So what's the connection? How does all this strange wave behavior have anything to do with reheating last night's pizza? Well, the answer reveals the secret behind why your microwave actually works the way it does. So inside your oven, microwaves are creating a big, three-dimensional stationary wave. And those nodes we talked about, the points of zero movement, they become literal cold spots where your food gets no energy. Meanwhile, the antinodes, the points of maximum movement, are super concentrated hot spots. Seriously, without that rotating plate, your food would cook in stripes. That rotation is absolutely essential to move your food through all the hot and cold spots to get it cooked evenly. And it all comes back to that perfect opposition. That 180-degree phase difference we saw, It isn't just some abstract number. It's the direct cause of those hot and cold spots in your microwave. This hidden physics is what makes that turntable so critical.
So the next time you see a guitar string humming or you're waiting for your lunch to heat up, you'll know the secret of the stationary wave. Kind of makes you wonder, doesn't it? What other incredible hidden physics is at play in the everyday objects all around us? Thanks for tuning in.